that's grouped together. So one of them is an x plus 2, the other one is
X.
and the last one is
Y.
So you're going to multiply top and bottom and change colors.
So X plus 2 times X.
X plus 2 times xy, right? So you take this entire top, you multiply it by xy, x plus 2.
See, that's what I'm saying, messed up on the paper.
And then you take the whole bottom and you multiply by xy, x plus 2. And you distribute it to every single term on the top and every single term on the bottom. Yeah, what's hard about this? So when you go over here and you hit this one, what goes away?
X plus 2.
The x plus 2, what stays around?
XY.
3.
The xy and the 3. So you get 3xy. All right, when this conglomerate hits 1 over x, what goes away?
Everything stays.
No,
Oh,
the x's go away
Y.
because there's one in the bottom, one in the top. So you get plus y, x plus 2. And then in the bottom, let's see, we're going to distribute that to the first one. So the y's are going to go away. 3x
X plus 2.
times the quantity x plus 2 minus, and then you distribute it here and you lose the x and you leave the 2, the y, and the x plus 2. And then you just simplify the top, simplify the bottom. Yeah. 3xy plus xy plus 2y over 3x squared plus 6. See, I like stopping at this one because I've seen people say 3x squared plus 6 and they forget that there should be an x. It's the weirdest mistake I've ever seen. Negative 2xy
Minus 4y.
minus 4y. Then combine what you can. 3xy plus xy is 4xy plus 2y all over. Good God, nothing combines in there. So you get 3x squared plus 6x minus 2xy minus 4y.
Okay, so when
Well, they actually broke it up into other stuff.
Yeah, I'm looking at it a little bit further. And the only reason I'm looking at it a little bit further is these two terms, there's 4 terms in the bottom, first of all, right?
That's what I was saying.
Yeah, if there's 4 terms, you can look for factoring, and if you pull out, what, a 3x in the first 2 and a negative 2y in the second 2, do you get the same terms? Let's find out. Bring it up. Let's factor the top while we're at it. What can I pull out of the top?
2y.
2y. What's left behind?
2x plus 1.
2x plus 1. And in the bottom, if we group and factor, we can pull out a 3 and an x out of the first one. That leaves behind an x plus 2. And we can pull out a negative 2y in the second one, and it leaves behind x plus
X
2.
minus 2. No, X plus 2.
Well, you're factoring on a negative, so you would divide it out. So it would be x plus 2. Oh, we can factor out x plus 2. Does it help us?
Well,
Not really, but, 2y, 2x plus 1, over, pull out that x plus 2, leave behind the 3x minus 2y. It would have been nice if something canceled and it all factored rather nicely. It's just, it didn't really help us.
so
So
you
that
could, if I would have had 2x plus 1 at the bottom also, they could have canceled out.
Yeah.
Okay.
Yeah, that's what I was hoping for, but it didn't work out. Now, I'm curious, did they write the answer this way?
Yes.
Okay. But since this didn't simplify, it looks a lot nicer. I'll give you that, but that also works fine.
Yeah, because they have it broken down all of 3 different things.
So, either way. This one actually does look nicer, though, if you can get to it.
I got some more.
What else? No?
No, I got one. Something. Like 1 over, x minus a.
Huh? 1 over x minus a? 1
Mm-hmm.
over x minus a.
Minus 1 over x.
Minus 1 over x.
All over a.
All over a. This is a very famous problem. You're going to see this if you get a little further in math. Was it? So, common denominator.
Yeah, I hated that one.
So x minus a, x and a.
X minus a, x.
Okay. Oh, it's over 1.
It's over 1. Why would I pick a?
You don't.
It's just x minus a and x. So you're going to multiply top and bottom by x times x minus a. I mean, if you want to write x minus a times x, that's fine, but usually you put the group things later. So when you distribute it to the first one, what goes away?
The xi.
And you're left with x. When you distribute to the second one, what goes away?
X.
The x, and you're left with a grouped x minus a. Over, and then you have to multiply the bottom by the same thing, don't forget that. And the only thing you could do in the bottom is write it. There's nothing to cancel out. Because it's just one at the bottom, so nothing to cancel. What happens in the top? That's the cool part. X minus x?
Would be 0.
Negative times a negative?
Positive.
So you get an a in the top, an ax, x minus a in the bottom. Am I done?
No, the a's cancel.
The a's cancel, what are you left with?
X, the 1 over.
1 over x minus a. That problem actually has a huge application.
Yeah, example was way
What's it used for?
They probably went for the common denominator in the top and then flipped and multiplied. It gets all messy. My way is a little bit quicker. And it reduces how many mistakes you make through the problem because you start getting common denominators for 2 sets of fractions and then flipping and multiplying. It just gets messy.
I got one from that.
This is just clean. You have one more?
Yeah. No, we don't want you teaching today. Look, we can't keep all this up, or you come in late every day and work the class. I'm trying to get my learning on.
Welcome, teacher Josh.
She said this is her first time.
If you don't have any more questions, I will teach.
I do. I was looking for it. Here we go.
It's just gonna take them an hour.
No,
No, he gets one more question, that's it.
5, 4.
there was one yesterday that took us like.
2.
Final Jeopardy.
More Josh.
You can ask later, Josh, when you find it.
I can't find it.
In the class would be fine.
I'll use that blue marker.
What's that?
That blue marker is about.
Yeah.
It's dry.
Here, we'll switch it out.
Oh, here it is.
Oh. See what you happened?
I know.
See what happened? You delayed me and here it is. What is it?
3 over 2x plus 1
3 over 2x plus 1
minus 5x plus 3
5x plus 3
over 2x squared
2x squared
plus 5x
plus 5x
plus 2
plus 2
equals 3 over x plus 2.
3 over x plus 2. I'll take a guess. 2x squared plus 5x plus 2 factors into x plus 2 and 2x plus 1.
Yep, it sure does.
Does it?
Yeah.
How do you know?
'Cause
I
did
saw
it
you
yesterday.
factoring yesterday. But if it wasn't, this problem would be horrible. And you can always check it after you write it down. 2x times x is 2x squared, 1x plus 4x is 5x, and then you get plus 2 at the end. All right, what do I do?
Just multiply everything by 2x plus 1 times x plus 2.
Just the top.
So if we multiply everything by these two factors, and I'm just going to kind of do this mentally, when it runs into this one, what happens?
You get the x plus 2 left over.
The 2x plus 1 goes away, you get the x plus 2 and the 3, so you get 3 times x plus 2 minus, now when this hits itself, one's on the top and one's on the bottom, it goes away and you're left with,
5x plus 3.
but this line represents
Parentheses.
parentheses, so it's parentheses 5x plus 3 is equal to, now when this hits this one,
We get that 3 times 2x plus 1.
Exciting.
oh, I've been Okay, so when 2x plus 1 and x plus 2 hit this one, what goes away?
Is x plus 2.
And you're left with
3 times 2x plus 1.
3 times 2x plus 1. Don't try to get it out of parentheses too soon, because that's when you usually make your mistakes. Get them out of parentheses, so you get 3x plus 2, what property?
Distributed.
I'm just making sure. Negative 5x.
Plus 6, maybe.
Maybe.
See, that's what you did this time.
Why? Minus 5x minus 3 is equal to 6x plus 3. Okay, combine like terms. Negative 2x plus 3 is equal to 6x plus 3. Add the 2x across, 3 equals 8x plus 3, and eventually you get down to x equals 0. Because the 3's cancel, you get 8x is equal to
Those were
0.
pretty easy, those ones right there.
But here's the problem. Can x equal 0?
No.
Yes. What can it equal? It can equal
X plus 2.
-2. Because if x is equal to -2, this becomes
0.
0. What else can x not equal? -1/2. So since that's not -1/2 and it's not -2, we're perfectly fine. There's our answer. X equals 0. Too many people think that that can't be 0 because you can't have x's in the bottom that are equal to 0. It's not the x's that are 0, it's the expression can't be 0. Now I can go on? Yay. All right, last section. We've had a vote to move the test to Monday. We'll do a little democracy here. I'm feeling Monday's a little bit better myself, so. You are not getting a test on Tuesday. Lab day.
What about Wednesday?
Why don't you give us a test in the lab on the computer?
We can go test in the lab.
No.
Why don't you let's take a test home?
Yeah, that's the best idea right there.
Wow, that idea will never float. Okay, so 6-5.
Just throwing ideas
Well, you
out.
tried.
You're gonna like it. It's got word problems.
No, I hate it. I hate it.
Everybody needs to get a chance to make 100.
To make one what?
100.
100?
Just one of them.
At least one.
You do on your labs.
Oh,
I mean,
I'm talking about on the test.
she's talking about on the test. Okay, so 6-5 is basically everything that we've already done. So I can go a little bit quick over some of the stuff, but not all of it, because it does get a little, well, strange. So let's start off with something easy. Number 8 on page, well, where are we? 339. And it says h is equal to xy plus xz, all divided by 4. And it gives a side direction of solve for x. Solve for x. Okay. Now, this has a ton of variables in it, and that's one thing that people don't like about these. It's like solving for formulas for a specific variable. Same idea applies. We did these earlier, but now we were creating fractions out of the mess, and sometimes the variable's in the top and sometimes the variable's in the bottom, where it becomes kind of dangerous. Because remember, if a variable's in the bottom, it cannot equal 0. I mean, if it's a single variable, like if it was 4x, x definitely could not equal 0. All right, so if we're going to solve for x, what do we have to do first?
Factor.
Multiply by 4. Generally, you don't want to factor because that creates parentheses. And usually when you're trying to solve a linear equation, you want to get rid of parentheses. So you multiply both sides by 4, and you get 4h is equal to xy plus xz. But Josh, in this sense, you might want to factor. Now, why would I want to factor here?
You want
Why
to
do
solve
I
for
want
x?
to, though?
You want to get x alone.
I want to get x alone. That's the only reason you would factor, is to solve for the variable you're looking for. So since both of these terms have an x in it, we're going to want to yank it out using what property?
Distributive.
Distributive property. So you kick out the x and you leave behind y plus z. This is the same reason that 5x plus 3x is equal to 8x. All right, how do I solve for x? Divide by
y plus z.
y plus z. You get x is equal to, I like putting the variable we're solving for on the left-hand side. It's called the reflexive property. You just take an equation and flip it around. And then on the other side, you're going to have 4h divided by y plus z. And there you go. There's your answer. That wasn't that bad, right? That's the answer. That's the answer. What else are you going to do with it? Nothing. You can't beat it to death. You can't manipulate it anymore. You got x by itself, and you got all the other junk on the other side. Nothing else to do. The only danger is if you have an x on the left and an x on the right. Then you're not done, because you need to get the x's on the same side and all the other junk on the other side. All right, so that one wasn't horrible. It's just warming you up to variable algebra. How about number 12? It gets a little worse. I know. E over little e, big E over little e, equals r, big R plus little r, divided by little r. and we want to solve for baby r. Okay. So if we're going to solve for baby r, what do we need to do first?
Need to.
Eat LCD.
And what are we going to do with it?
Multiply.
Multiply. Get rid of the fractions. You don't want to deal with fractions. You want everything on a straight line. So what are we going to multiply both sides by?
Even more.
ER.
Little e.
Little e, little r. So if we multiply this side by little e, little r, and multiply this side by little e, little r, what are we left with? Well, over on the left, the e's are going to cancel, and you're left with big E, little r. Or little r, big E. It doesn't matter what order you put it in. Equals. Now, on this side, when you multiply ER by this R thing, what goes away? The little r goes away, and you're left with
Big R, little e. Little e.
E times R plus little r. So I'll just write that out. E times big R plus little r. Sometimes these are easier because you don't have to worry about calculations. All you're doing is moving letters left, right, up, down. But you're not doing any calculations whatsoever. Now, always go back to your goal. Your goal here is to solve for little r. Where are they? Well, one's on the left, and the other one's on the right, and it's inside parentheses. So what do we do next?
Distribute.
Distribute. Get it out of the parentheses. E big R plus E little r. All right, again, the focus should be on the little r's, which are here and here. Where do they have to go? Might as well move them both to the left. So if we move the little e r over here, you're going to have big E, little r, minus little e, little r, is equal to little e, big R. So when you shift it over, remember it changes its sign because you're subtracting it from both sides. Again, your focus should be on your little r's. At least they're on the same side of the equation now. What can we do next?
Divide by little r.
If you divide by little r, r has that possibility of being 0. You cannot divide by 0. Never ever divide by the variable you're trying to solve for. Factor it out, just like we did over there. So if you pull the r out, little r out, you're left with big E minus little e, and this is equal to little e big R. All right, and finally, how do I solve for r?
Divide by.
Divided by the e's. So we're going to get r is equal to little e big R divided by big E minus little e. Question of the day, can you cancel out the little e's?
No.
Please don't. Why? Because there's subtraction. Because there's no multiplication all the way across the top and multiplication all the way across the bottom. So there's your answer. That's it.
So if it was big,
What do you mean? If this was a
Like-
big E,
no, if it was here.
if this subtraction sign was not here, it would be big E times little e, then you can cancel the little e's. Guaranteed. But because the subtraction's there, you don't touch a thing. Alright, how about an ugly one? Number 26. Little e equals L R sub 2. When you write a little number underneath it, you know, if you write it above, it becomes r squared. But if you write a sub number, it just distinguishes r sub 2 different from r sub 1, which is different than r by itself. So it's just a way of saying the same variable, but it actually is a different one. So if I write r2, it'll be the same as this. But if I write r1, it's different than this one. All right, over r sub 2 plus r sub 1. And we're going to solve for r sub 1. So even though the letters are exactly the same, the sub numbers are telling you that they're actually different. This is pretty much saying this is the first r, this one is saying it's the second r, like you're doing two measurements or something. Okay, so if I'm going to solve for r1, what do I have to get rid of first? The fractions. Got to get rid of the fractions. You can't leave things lying in fractions because we're trying to solve for a variable that's in the bottom, and you can't do it while it's in the bottom. So multiply both sides by r2 and r1. And multiply this side by r2, r1. Or r1, r2. It doesn't matter which way you order it. All right, so when we come down on the left-hand side, we will have D times R1, R2, I'll put them in order here, is equal to, what happens on the other side? Oh, wait a minute. Yeah. Plus, I gotta erase some stuff there. This is horrible. It's supposed to be plus. Because the common denominator is R2 plus R1. Okay, so on this side it's actually D times the quantity R2 plus R1. I'll leave the order here. Equals. On this side they're going to cancel out, and you're left with LR2. Again, go back to this and say, oh, that's what I'm solving for. Because sometimes you'll start working it and you'll forget what the heck you're trying to do to begin with, and you'll go in circles. So go back here, you're trying to solve for R1. R1 is right here. What do I need to do? Distribute. So you get dr2 plus dr1 is equal to LR2. Now what?
Subtract out the dr.
So dr2, right? So move this piece to the other side, and we're going to get dr1 is equal to LR2 minus dr2. Now, if you want, you can factor out the the R2s, but you don't need to because that's not what you're trying to solve for. You're trying to solve for R1. You start factoring out R2, and all of a sudden you start solving for R2, and things get weird. You're trying to solve for this variable over here. So the only thing I need to do is divide by D, and you get R1 equals fraction D in the bottom, LR2 minus dr2. And you're done. So those aren't horrible. They're just manipulating fractional expressions. And always divide by the common denominator, or multiply by the common denominator, and then get rid of fractions. And the only time you want to create fractions is if you're trying to solve for a variable and it lands in two different places. So the only way to create one instance of it is to factor it out. That's the only time you do it, and it's usually at the very end of the problem. All right. Word problems. Number 40. So before I start, this actually has its own little title. It's proportions. And proportions, you can think of them as percentages. Percentages are technically proportions. But proportions are if you have any two fractions, and those two fractions happen to be equal to each other. This is where that terminology of cross-multiplying comes from. It's the only time you can ever say the words cross and multiply together, because it only works in proportions. So if you're going to do a proportion, you would multiply A times D, and it would be equal to B times C. So what's neat about proportions is they're either two fractions that are equal to each other, or it's the product of two numbers is equal to another product of two numbers. That's also considered a proportion, because I can always go back to fractions. So sometimes in applied math, you'll find that you have the product of variables next to each other, and you want to consider that a proportion because it's easier to think of it as fractions. So it's kind of a neat little trick. All right, what things happen in proportions? Do we use proportions? Did you drive here today? You didn't? You walked? That's why. If you drove here today, you had to keep your eye on something, right? What was it? Gas. You're going to run out of gas every 5 seconds. You're speeding. And speed is measured in miles per hour. Anytime you say the word per, you're actually working with a proportion. So let's say you were doing 75 miles per 1 hour. Wow, you drive fast on a 35.
I take the interstate.
So how long did it take you to get here? 20 minutes. So you drove 20 minutes, which is 1/3 of an hour? Okay. So then you put 1/3 of an hour up here. And if you multiply that, well, that's not really a proportion. Oh, actually, yeah, it is. Hold on. Let me back it up. I got to change it to a proportion. I'm thinking algebraically.
I thought that's what we're doing.
Proportions. No. Proportions in algebra are a little slightly different. So we're going to set this equal to, you drove 1/3 of an hour. And what I'm curious about is, how far away do you live? Now, that's assuming you drove 75 miles per hour from the driveway to our parking lot, which doesn't happen, but that's a huge assumption. So, how do I solve this proportion?
75 times 1/3.
So you go 75 times 1/3, which is nice, it's 25, right?
Yeah.
So that would be 25, and that would equal X, yeah. So you live about 25 miles away? Give or take. So it's kind of neat. So proportions are miles per hour, dollars per pound, feet per second. Anything that you say the word per, you can always set it up as a proportion to solve for unknowns. Another common way of writing them is something like this notation. This is read 2, 3. In other words, I should have done it for this class, but that's okay. Let's say there are 2 men for every 3 women at a college. And I know that there are 70 men. My question is, how many females are there? And the way you set this up is you take the 2 to 3 and you write it as your fraction, where the top is males and the bottom is females. Proportions always have an order. You want to match them up straight across. Just like over here, I had miles and miles on the other side, hour on the bottom, and hour on the other side. You want them to match up, because we're usually dealing with direct proportions. All right, so we have 2 to 3 is equal to, well, how many men do we have? 70, so he would go up top. How many females do we have? No idea, so you call it X. And you set up a nice proportion. You cross multiply. You get 2x is equal to 210. And therefore x is equal to 105. 105. So there would be 105 females. So there's some neat little applications to it. Yeah, these are nice word problems, aren't they? Yeah. Wait until you see some. Pretty much. Number 40. This is where it gets a little messy. 40. The setup is no different. They give you a proportion, or they tell you something about what's going on, and that becomes your first fraction. The second fraction is the question they're trying to answer. So at Elmwood University, there are 9 men for every 5 women. You can write that as 9 to 5. Men, women. Okay. There are 182 faculty members. Now, when I say there's 182 faculty members, it's made up of men and women, so they're not being separated. They want to know how many men and how many women are faculty members here. So, what do? Well, the first thing you have to do is designate what your X is going to represent. Over here, obviously, the X represented how many females there were. So what do I want X to represent over here? One of them. You don't want to say both. You want to say, well, I know how many both. It's 182. You either say it's the men or you say it's the women. It really doesn't matter which one you say. So which one do you want? Women. All right. So X equals number of women. You really want to tell your word problem what the variable represents at the beginning. Because by the time you get to the end, you forget what X is all about. Who did I see that on a test paper with?
Not mine, or
Yeah, So, we'll set it up. It's 9 men for every 5 women, and that's going to equal. Now, when we set up the other fraction, women is X. So where does X go in my problem? The bottom, because it has to match up with the women over here, the 5. So there goes x. Now my question is, what do I put for n?
182. Going to put the 182.
182 is everybody.
X subscript 1.
You could put y up there, but then you have two variables and it's really hard to solve for one variable.
X minus 182.
Close, no cigar.
X go 1 above.
182 minus x. Because you have a total of 182 and you used up x of them as females. So this would be 182 minus x. And then you get a nice little proportion. How do you solve it? Cross multiply is the only time you can do that fraction. You can do a fraction. So if you cross multiply, you're going to get 9 times x is equal to 5 times the quantity of 182 minus x. So 5 times 182 minus x. And it becomes a nice linear equation. Pretty simple. Distribute the 5, and you get 9x is equal to 910 minus 5x. Add 5x to both sides, it becomes 14. 14x equals 910, and I'm assuming that 14 goes into 910 nice and evenly. 65. So when we get down here at the end, this is 65. 65 what? Women. So, women. And how many men? Subtract it from 182. So, how many? 117 men. And that's it. I always thought these problems were kind of easy. Because all you do is set up a proportion, cross multiply, and solve a simple linear equation. Do they get hard? The only thing that gets hard is trying to figure out the order of the numbers and making sure you keep them exactly the same, like men to men, women to women. Oh, so can I make it harder? Yeah, sure. No, we don't do this in 161. That's the beauty of it. We don't do proportions that much.
You want to do word problems?
We do tons of word problems so that they become much more complex. And I get more happy. Number 46. This is a geometry one, so I got to teach you a little geometry. Couple of pictures. Let's draw this one first. If I have a right triangle, and I draw a line perpendicular to the base anywhere from the hypotenuse, what happens is we get 2 triangles out of it. Well, actually 3 triangles out of the deal. No, just 2. 1, 2. That's it, 2. And what happens is these 2 triangles, let's color this one in black. And this one in green. These 2 triangles have a neat property. And let's separate them. So we have this big green triangle. And we have a little black triangle. Let's black mark this time. I write too much. Let's write this in. Okay. These 2 triangles are considered similar. Remember similar from high school geometry?
No,
I didn't think so. And the reason they're similar is because they share this angle down here, so both of those angles in that part of the triangle are equal to each other. And they both have right angles, therefore they're similar, which means their sides are in proportion. So if we label this A, B, C, and label this one C, D, E, then if the triangles are in proportion to each other, I can write a fraction like A over B of the first triangle, and it's going to equal the same pattern on the other side. So this is long leg to long leg, which over here would be C, which would be A. B is short leg, and over here the short leg is D. So this would be D. So you get A over B in the first triangle is equal to C over D in the second triangle. In other words, if you took a magnifying glass and you used it on the black triangle and made it as big as the green one, they'd be the same triangle. It's just a scaling factor that's changed them. All right, that's one possible type of similar triangles. Another one happens if you have any old triangle, scalene triangle, and you draw any line that is parallel to the base. So these two lines are parallel to each other. If that happens, the two triangles are similar. The top little baby triangle and the bigger triangle are considered similar. This one's a trickier setup. So if I separate them out, and let's call this one the blue triangle, and the other one the green triangle. Hard to draw. And we call this side A, B, C, and this one D, E, F. I used C twice over there. I just realized that. Call the side F. So that would make this F. No one told me that.
I'm sorry, I thought maybe I was
Yeah, but if I use the same letter twice, no, that's not good. The same thing happens. If I write A over B over here, what would it equal in the other triangle? D over E. So because these two are also similar, it's not as easy to figure out that those two are similar compared to this one. But if you have parallel lines, this angle is equal to this angle, and this angle is equal to this angle. They're called corresponding angles. Remember that? Corresponding. So these are proportions that we can use with triangles. One of the major uses of this type of proportion is number 46. Number 46 says a 3.5 foot tall child casts a shadow that is 6 feet long. At the same time of day, a tree casts a shadow that is 42 feet long. Okay. So if you're going to draw this, you're going to have a base, some ground, and you're going to have some kid standing there. How tall is the kid? 3.5. 3.5 what? What is it? Shortcut. So you have this 3.5 foot, 3.5 foot kid standing here. How do shadows get cast? Is the sun straight up in the air?
No.
No, because then there's no shadow cast, it just goes straight down. So the sun is kind of off at an angle over here. So I'm going to put the sun over here. And he's shining down, and it hits the kid, and it creates a shadow on the ground. So the only thing I know is his shadow is how long?
6 feet.
6 feet. So the base here must be 6 feet. I've had people put the shadow here on the hypotenuse. Shadows always fall on the ground. I don't know what they're thinking. Maybe the shadow in the air. Then you have a tree under the same situation. And you have your ground. And your tree is standing someplace. Like this. And it has the sun up here someplace. And it casts a shadow. How long is this shadow? 40-some?
42.
42. 42 feet. Okay. Now my question is this. Are these triangles similar? Why?
Because you could fit into the triangle.
Yeah, but why? How do I know they fit exactly? It's in the words if you read it correctly. 3-foot child casts a shadow that is 6 feet long at the same time of day. Why would they have to say that? The same time of day. Yeah, the sun's at the same angle. Therefore, the angle here, whatever this angle is the same angle it is here because the sun is at the same angle during the same part of the day. Okay, so what's the unknown piece here?
How tall a tree is.
How tall the tree is. So if this is our tree. We're curious about how tall it is. All right, so how do you set up the proportion? 3.5 over 6 must equal x over 42. Wow, this is the easiest word problem in the world. Cross multiply and solve. So 6x is equal to, I don't know, 147. And if you divide both sides by 6, it does not come out nice and even. Sadly. Not horribly though. X equals what? 24.5. Short tree. My tree was 100 feet.
You have to draw.
What's that?
You have to draw.
Oh, that gets dangerous. You start not drawing pictures and you assume the pieces are where they are, you'll set up a proportion and it comes out wrong. But yeah, in that case, maybe a simple one you might not have to draw, but my suggestion is draw it. I mean, all you're doing is drawing two triangles and making sure your sides line up. The reason for that is some of these triangles, they'll fool you into thinking one side corresponds to another. It doesn't. So you gotta be really, really careful. But for the most part, they're gonna be nice and simple. Yeah, you probably could guess at it. But then what are you doing? Guessing. Guess what math test? New employee at Pete's Yard Service can mow 4 yards in 5 hours. Pete, the owner, can do the job in 3 hours. How long would it take them to do it working together? First off, do you care if he can mow 4 yards? No. What you're concentrating on, it actually comes part of the second part of the sentence. Pete, the owner, can do the job in 3 hours. He didn't even talk about 4 yards. He just talked about a job. So the one thing that's interesting here is you're only concerned about one job. Everything comes back to finishing one job. All right. So Pete can do it in 5 hours. So Pete can do the job in 5 hours.
3?
Pete?
Yeah.
Oh, I'm thinking, wait a minute.
Pete's employee.
Pete's employee. Pete can do it in 3 hours. Pete's employee, they didn't name him? Employee. He can do it in 5 hours. So the question actually boils down to this. How much of the job can the employee do in 1 hour? How much of the job can he finish in 1 hour? I'm asking you, if he can finish the whole job in 5 hours, how much of the job can he finish in 1 hour? 1/5 of the job. Yes, 100%. I'd rather the fractions. So, employee can finish 1/5 of job in 1 hour. That tells you a lot. Because how much of the job does he get done in 2 hours? 2/5, 3 hours, 3/5, 4 hours, 5, and so forth and so on. Okay, how much of the job can Pete get done in 1 hour? 1/3 of job in 1 hour. So if I ask you how much of the job gets done if they work together in 1 hour, what would you do? Add 1/5 and 1/3. So part of this becomes you're going to take a 5th and a 1/3 and you're going to add them together to find out how much of the job you're going to get done. Some kind of 5th and some kind of 1/3. How much of the job do we want to get done? A portion of the job? The whole job. So this has to eventually equal a whole job. How many jobs? One. One whole job. See, if Pete can do 1/5 of the job in 1 hour and 2/5 of the job in 2 hours, I'm not sure together how much they're getting done. But I still want them to get one job done. So how much time does it take for them to get the job done together? Do you know? So what do we call it? X. So X equals time together. How long does it take them to do the job together? Now, if they work X hours, how much of the job does the employee get done? Why do people get confused about this? How much of the job does he get done in 1 hour? 1/5. 2 hours. X hours. X fifths. How much of the job does the boss get done in X time together? X thirds. And then you have a nice little equation. No matter what the time is, he's going to finish a fifth of it, a part of a fifth, and this one's going to finish the part of the third, and together they're going to add up to be 1. How do I solve this? Common denominator, which happens to be 15. Multiply everybody by 15. Once you got it set up, boy, this is quick. 5 goes into it, this will be 3x. 3 goes into it, this will be 5x. Don't forget to multiply the 1, which gives you 15. Because if you leave it as 1, and I think it ends up being like negative time or fraction time, which is ridiculous. And then 8x equals 15. And x equals decimally 1 7/8 of an hour. What is it? 2.25.
1.875.
Well, how did you get 8 times 2 is 16? This is 115. 1.875 hours. Okay. If I tell you it's going to take you 1.875 hours to drive from here to Greenville, you're going to say, what? So how do I find out how many minutes 0.875 of an hour is? Multiply by 60. So go ahead, what's 0.875 times 60? 1 hour. Yeah, well, 52. 52, or rounded? 53. So it would be 53 minutes. 1 hour and 53 minutes, and they will finish their job together. I like word problems that say they start the job at 1 p.m. When do they finish? And then you do have to convert it into minutes because otherwise you'd be like, it'll be 2.875 p.m. Do you have time for one more? Yeah, I do.
No.
Since we missed the class, I have to catch up a
Let me
little
see what time it is.
Number 50. It's a slight variation on that one. It's a slight variation, but the setup is technically exactly the same. A lumberjack and his cousin. Why did they do that? Lumberjack and his cousin Fred. Why can't they give them both names? It would make life so much easier. Can split a cord of seasoned oak firewood in 3 hours. So together, they can do the job in 3 hours. Okay. Without any help from Fred, the lumberjack can do it in 4 hours. So by himself, 4 hours. Okay. How long will it take Fred if he worked without the lumberjack? So in other words, Fred becomes X hours. Now the setup is identical to this one, but the only difference is X is now not going to represent the time together because over here we have the time together. But the setup is going to be the same. You're going to have a fraction plus another fraction, and it's going to equal 1. Where X is over there, we now are going to put 30 because their time working together is 3 hours. So 3 goes here, 3 goes here. Now, we just have to decide which fraction is the lumberjack. Just pick one. It doesn't matter. First one. All right, so here's my lumberjack. By himself, he can work, do the job in 4 hours. So where's the 4 go? In the bottom. What goes below this 3? X. And there's your setup. Only one variable instead of 2 separate ones. So we're going to multiply this whole thing by 4x. So when we multiply the first one, what goes away? The 4, and you're left with 3x. When you multiply the second one, what goes away? And you're left with? And the last one, don't forget him, gives you 4x.
Wow, he's slow.
Yeah, he is slow. Subtract 3 and you get x is equal to 12. So by himself, it takes him 12 hours. Lumberjack is really good. Fred's a little slow. He keeps breaking the chains. He's just a split off the street. All right, homework.
Oh, no. You gotta go.
Test on Monday, so